Uh, Hello, everyone. It's a pleasure to be talking with you this morning. Let me just get my screen shared. So can everyone see that okay?
Yes.
Excellent. Yes, so the first thing to say, so my name is Martin Dallimer. I'm based at the University of Leeds, and I've worked for a number of years now with Bob Cheek, who I guess many of you will have come across talking to this forum before. And the presentation I'm going to give you today is actually work being undertaken by Rachel Dobson, a PhD student of ours at the University of Leeds, together with colleagues at Leeds, Andy Challoner, and at Durham, Steve Willis. So I will give the presentation, but if there's some technical information that you need further details on, I may or may not be able to answer those questions depending on what it is that you want to know. But all of this work here is Rachel's, so I cannot take the credit for any of the modelling that she's been up to. So, as we've been hearing, early warnings, one of the things that we've been interested in trying to do is understand how we might be able to use existing data on quelea and current data for quelea to develop an early warning system for the bird. And as we've been hearing, migratory crop pests threaten food security worldwide, and there are plenty of examples: locusts, armyworms, as well as quelea. And the challenges to managing these species are their highly variable distributions and their rapid population growth. And as we've been hearing, a lot of the current management is around lethal population control in response to crop damage being reported. So this then leads to potentially quite a lot of damage happening before the birds are controlled, or the crop pests are controlled, and also a lot of potentially damaging chemical use. So how do we think about advancing management? One way we could do that is through having an early warning system that can forecast crop pest risk and therefore inform decisions that are taken regarding management or regarding planting prior to that damage taking place. And this is where the idea of an early warning system comes in. So forecasting the crop pest risk, so policy and management decisions can take place prior to any damage happening. If we're going to have a good early warning system, it needs to be reliable. It needs to have value to those forecasts. It needs to be easy to understand, and it needs to be freely accessible to all. And examples include the Desert Locust Information Service and the Fall Armyworm Monitoring Warning System, both put together by FAO, but both have some limitations. So for the Desert Locust Information Service, there's some limitations regarding its reliability and the cost of the weather forecasts that are required. And for the Fall Armyworm Monitoring System, requires the smartphone access to the internet and so on. But still, the idea of early warning systems for migratory crop pests is well understood, and the value of them is potentially considerable. So we wanted to then work on quelea as another migratory crop pest for which this approach might be appropriate. So as we know, quelea consume cereal crops, they're nomadic, and as we've been hearing, are hyperabundant. And they also have high intra and inter-annual variability, which is part of, therefore, why an early warning system could be quite valuable, because farmers don't necessarily know that every year they're going to be subject to a quelea outbreak. As these graphics here show, where and when quelea occur during a year is highly variable. And also, as we've been hearing, current quelea management largely relies on pesticide sprays, on fire bombs, and some of the alternatives that we've been hearing about: drones, falconry, altering crop planting schedules, choosing different crop species to plant depending on how vulnerable a farmer may feel they are to quelea infestations. And the challenge then is that currently there is no early warning system for quelea, except for some qualitative bulletins that may get issued at different times of year and in different places. So how then can we go about developing an early warning system for quelea? And what we've done, or what Rachel has done, she's taken historical quelea data from 2000 to 2019, and that's occurrence and abundance records from pest control services and also from citizen science initiatives such as eBird. She's combined those with remote sensed predictors such as short-term weather conditions and access the predictions of resource availability for quelea. So these are, we generate these through crop models and also grass production models. And we can use these then, or Rachel can use these to model the ecological relationships between where quelea occur and the abundance of those quelea and weather and quelea resource availability. And she's used some very advanced modeling techniques that combine different regression approaches and machine learning to develop some ways to begin to start to understand how feasible it is to develop an early warning system for quelea. She then tested some of this work by excluding the 2018-19 data from the training data that she's working on and using 2018-19 remote sense variables to then try and see how accurate the predictions of the model may be. And she's evaluated this using what she's called a gold standard, using remote sense data, and also the occurrence and absence records from 2018 and 2019. And this is a graphic which shows the what quelea are up to in this historical period. So you can see again, highly variable. This is breeding, distribution, and abundance data. Highly variable occurrences, both spatially, as you can see on the left, and temporally through the year. This is for breeding distributions. And then this then is some of the outputs of the modelling that Rachel's been undertaking. And for what she's called the gold standard approach, which is the one with the green box around it, which has a higher resolution than the forecast in the purple box on the left, she's managed to achieve an 84% accuracy of her model. So that then encompasses both true positives, so where the model forecast quelea to occur and where they actually were, and true absences, so where the model forecast quelea to be absent and where they were actually absent. So 84% accuracy is good, it's a good start, and we feel one of the next steps then is to further work on how we can improve the accuracy of these predictions, and also think about how we can start making them accessible to end users. So this modelling approach then clearly has some promise for quelea management. So if we're able to finesse this a little bit further, I think the early warning system will be able to say where quelea will be abundant in a specific area at a specific time of year. So this then potentially could allow farmers to switch to quelea resistant crop varieties or species, to alter planting dates to create a timing mismatch between when crops are vulnerable and when quelea might be present, and also to get in place survey and monitoring protocols which ensure that quelea colony formation is picked up early, so any control can take place before any damage is done. And the benefits of this might be to reduce pesticide use, to improve the efficiency of any control mechanisms that are undertaken, improve food security. Our challenges remain the ecological challenges. So how do we improve the modelling forecast based on those remote sensing variables, the forecast of climate in terms of the resolution and accessibility of these data, and then practical challenges. So how do we ensure that models are updated so they remain useful, and how do we go about reaching stakeholders and users of the potential forecast to ensure that data are available, information is available in a timely way that ensures that management decisions, farming decisions can be taken that can help minimize quelea damage. So just then to summarize, so early warning systems could considerably improve quelea management and protect food security. And our ability to develop an early warning system is really being driven by improvements in the quality of data and the quantity of data that we have available to us, as well as the kind of technical side of the computing power that allows some of these complex modeling processes to be undertaken in a much more straightforward way than even a few years ago was possible. But if any of this is going to be useful, we need to ensure these forecasts are accessible and also in a usable form to any potential end users and stakeholders. So that's everything from me. So when the time comes, I'll welcome any questions. And it's just really, again, to emphasize that this work is certainly being led by Rachel, and this is the list of our team members that are supporting Rachel through this process. So thank you ever so much.